like me to continue? Should I get started? I've titled this Ocean-Based Climate Solutions, but I'd like to start by just talking a bit about, oh, my slide's not advancing. Hold on. There we go. I just want to start by talking about Oceanography Canada first. And the motivation for Oceanography Canada stems from the fact that, as most of you, all of you know, satellite images get the surface of the ocean and they don't get the sea, what I call the sea beneath the surface. So that provides us information about the global conveyor belt and other things. And as all of you know, in oceanography, it took decades for us to understand the large global conveyor belt. And so at the University of Victoria, there were two mavericks here, and there were some mavericks at the University of Washington at the time who said, let's put some sensors in the sea beneath the surface to understand the dynamics of that volume of water that sits beneath the sea surface. And so that was the motivation for, at the University of Victoria here, Chris Barnes and Marina Tunnicliffe to propose to develop an observatory system of the sea beneath the surface about everything in the ocean: physical oceanography, biological, the interaction with the continents. And because it started on the West Coast, we have this incredible dynamic seafloor, including a spreading center, a subduction plate, all the associated dynamics of that. And so what they proposed to build was a telecommunication cable system. And that was a concept that was developed by John Delaney and Deb Kelly at the University of Washington. But because of mostly politics, Canada was able to move forward first with this large telecommunication cable systems, starting with two observatories: NEPTUNE, which is shown as 900-kilometer long telecommunication cable, and Venus, which is two cables, one inshore, close to the shore, in Sandwich Inlet and in the southern state of Georgia. As next month, on February 8th, we'll be celebrating our 15th anniversary as providing real-time data 24/7 from these networks. But what this is, there's nodes here, and there's extension cables that come from those nodes that now host thousands of sensors delivering data 24/7. And this footprint represents a very big range of ocean environments: a spreading center, abyssal plain, hydrate-rich continental shelf and slope, very dynamic wave-impacted coastal area, and then in the southern Salish Sea is a human-impacted waterway. And then in Sandwich Inlet, it's a natural low oxygen environment. So if you are studying any activities in those kind of environments, you can use this data in real time without it's all open data for you to use in research. And we have about 50% of our scientists are from outside of Canada and 50% from Canada that use this infrastructure. We also built our own digital infrastructure called Oceans 2. We are a national research infrastructure. We collect data from thousands of sensors, and we have autonomous data analysis systems, as well as we provide full open access to science, society, and industry following Canada's open data policy. And that open access is through downloads, through interaction with our website. We can do web services, automatically deliver data for tailored to anyone's use. And because of that data system, we have expanded our observatories to include coastal observatories along the British Columbia coast. I'll come back to that in the Arctic. And now we're expanding to the east coast of Canada. And soon we'll be expanding into Hudson Bay. And that's because we have this really rich digital infrastructure that allows us to capture data from a cable, from satellite, from cellular, from point to point, in any way that we can bring the data into the data management system. We're funded by the Canada Foundation for Innovation. They provide us 40% of our operating funding. These are just our science themes, obviously very clear: climate change, life, seafloor, ocean, atmosphere links, and of course, seafloor motion, which is all about that tectonic and dynamic rich ocean environment. Just to show you a couple images, this is just an example of the gas-rich continental slope where these crabs are feeding on microbes. And as many of you know, when methane hits a certain object, it forms hydrates, and the hydrates are lighter than seawater, so it causes the crabs to flip upside down. And so they go to these feeding places probably for food and for fun. And this is just an image of one of our nodes. They're about as big as a large size office building. And this is the spreading center, the Endeavour segment of the Juan de Fuca Ridge that we monitor 24/7. And this is 320 degrees C mineral rich water hitting the ocean and building these black smokers, and life forms on them. So there's research associated with the origin of life. How do these hot vents interact with the oceanography? And this just shows you the environment for, that's a cable that's delivering both power and internet connectivity to the sensors at this location. But what I really want to talk about is what we have moved towards is, so we're very similar to the Ocean Observatory Initiative, but different from the Ocean Observatory Initiative is that we are required, and rightly so, using public dollars, to also deliver.
You want me to have a share?
Wait. I'm in class right now.
Huh?
I'm in class right now. No, don't worry. Bye.
Can you hear me okay?
Yes, Kate, sorry, somebody had unmuted their microphone by mistake. Corrected.
Yeah. So somewhat different than Ocean Observatory Initiative, which is really built for delivering research data, as we are. We are also asked to actually deliver what's called broader benefits to Canada. So we develop data products we have them in 3 buckets: ocean safety, ocean health, and now climate solutions. I'm just going to give you a couple examples in ocean safety and ocean health, and then give you examples of what we're moving forward on climate solutions. And so in terms of ocean safety, we have tsunami and storm surge is one of our big products and where we're moving towards. We also have installed earthquake early warning. We also have a sea state alert for marine safety. But I'm just going to give you an example of the tsunami. So I just explained to you we are in a big subduction zone where tsunamis occur. This is just an animation showing you, and I know most of you know this, that subduction earthquakes cause tsunamis. And as does underwater landslides, we have a delta dynamic experiment where we're actually trying to understand the generation of tsunamis from underwater landslides. And we have, this is just a diagram showing you the timing of an Alaska earthquake that happened several years ago. But our real-time data goes to the Pacific tsunami warning system. So that's used to actually provide information for the alerting and the stand down of any kind of tsunami wave. But more importantly, we brought scientists together, seismologists, tsunami modelers, together with our data to actually develop models of forecasting the tsunami. And this kind of scale, this is Vancouver Island in Washington, the west coast of the Pacific west coast of the United States, is really important for research. But what we did further was we took it to another level. This is an inlet called Port Alberni. It's on Vancouver Island, and it was the only town that was impacted by the 1964 Alaska earthquake. And so we worked with tsunami modelers, particularly those from Rhode Island that Matt Horn is from, where we integrated digital elevation models with the tsunami inundation model at high resolution to actually provide information for the town. And on the right is the map of the emergency response map. So the town then used that information to plan where the caches would be, the escape routes, and they're using it for long-term planning in terms of where they should be building municipal systems, et cetera. And we're moving in this direction for this kind of work, but also for storm surge that I'll talk about in a minute. Ocean health, I'll just give you one example. We're worried about noise. This cartoon just shows you that here in the southern Strait of Georgia, there's the southern resident killer whales are endangered, and one of the big stressors is noise. So what we did was we worked with the Port of Vancouver to install a ANSI standard hydrophone array where we captured source signatures of ships to be used for model purposes. I hope you can hear this. This is how we normally use the data. That's these are big killer whales. This is the sound and the sonograph. That was the sound and sonograph from the ship source signatures. We've captured over 3,000 ship source signatures at ANSI standard. And then they're used by a company, JASCO, who's an excellent company in terms of acoustics and modeling. And JASCO pulls the AIS, the ship traffic data from our data management system, Oceans 2, maps it to that source signature of sound, and then can model in real time the sound signature in the Southern Salish Sea. So now the port is using this not only to manage the ship traffic to reduce noise, but also to provide lower fees for ships that actually reduce their noise over time. So that's just one example of the noise product. Now I'll jump into the climate solutions. We are just starting to work on ocean renewable energy. We're starting to discuss with mainly offshore wind farms how we can couple essentially research quality nodes and extension cables like I showed you on Neptune and Venus to couple them with this growing number of offshore wind farms. But we've just started those discussions and we hope we can move in that direction in terms of providing scientific data in collaboration with offshore wind. In terms of ocean acidification, I'll talk about these three in order. In terms of ocean acidification, everyone knows that as we absorb CO2 into the ocean, it becomes more acidic through chemical reactions. And this is a map of southern Vancouver Island. You can see the city of Vancouver on the right, so to orient yourselves. And that yellow box shows that we have a mooring, a cabled mooring in the area called Bain Sound. And Bain Sound is the location of the largest shellfish aquaculture industry in British Columbia. So we took an unused buoy system that we had in our shop, and we refitted it for measuring ocean acidification, pH, PCO2, and all of the other water quality properties, delivering in real time. Our next step is to expand the sensor system on this buoy to include harmful algal blooms with flow cytometry, and also for pollution purposes, because there's a lot of ships around here and there's accidents associated with bilges being spilled into the waters. So that's going to be a really wonderful information for the aquaculture industry. They're currently in a lull because of COVID-19. So as that industry picks up again, we will be developing data products for them in real time. And of course, it's really to protect this wonderful industry where we all love to eat, most of us love to eat these delicious oysters. And of course, the research purpose is to try to understand the impact of ocean acidification on the entire food web. So it's both our research platform and we hope to be delivering data products right to industry. I'm going to talk about Indigenous engagement in terms of the climate solutions, because Canada has made commitments to actual Indigenous communities participating themselves in data collection for their own purposes in their coastal communities as climate change impacts the coastline. What you saw in the beginning of this animation was Cambridge Bay, Nunavut, which is one of the northern Arctic communities in Canada, a quite large one. And in 2012, we decided to see if our technology could actually work in the high Arctic. And so we took a small platform, cabled it to the shore, and installed our normal sensors that would go on a water quality camera, hydrophone, and we also added a sea ice thickness measurement device. And we were successful. It was working quite well. We had a small data pipeline through satellite, and that was working fine. But what we learned was that the town wanted the sea ice thickness data shown in real time on the co-op store, because they are concerned about the loss of sea ice and wanted to have the information so they could safely travel to hunt, to take a shortcut to the airport on the ice. And so that was our big aha moment in 2012, where we started to actually develop these observatories for communities. This is a picture of one of the earlier versions. They're now much more compact and standardized as we've built more and more of them. But as we then started to move forward, we engaged the entire community, and we hire youth science ambassadors in the community that then help the community understand that science and technology in these small observatory systems. And then we develop data products that they're specifically interested in for their own use. And the woman in front of the rectangular window there, Mia Tokiak from Cambridge Bay, she was there when I think she was 13 when we first installed the first one. And she graduated from high school, which is a big milestone, and now works in science for the Nunavut government. And we then couple that with a program we call Community Fishers, which is a standard oceanographic instrument, CTD. All the fishers, and this picture doesn't show Indigenous peoples, but most of the Indigenous peoples use this system with the tablet to go to their regular fishing grounds on a regular basis to do these casts of a CTD They don't have to do anything about except lower it and bring it back up. The data gets transmitted to the tablet.
I think we may have lost Kate.
Internet connectivity, all the data goes to our data management system, has allowed to power many, many communities in Canada that need the data, not only to make decisions about their own changing coastline, but also to empower them to have the ability to talk directly to the government about their needs. So this is a map all over Canada of the communities we're now working with. And this particular community engagement is growing quite a bit. But as sea level rise happens, as coastal storms increase in places like the Arctic, where ice is forming later, and as water quality changes with ocean acidification and pollution, they then have their own information to actually help them make decisions about mainly issues associated with climate change. But I'll say one more thing about our engagement is that what we hear over and over again is that the number one issue that that these communities are interested in is having their kids exposed to science and technology. In terms of other products, I mentioned the tsunami work. We actually now are moving towards understanding the impacts of sea level rise and storm surge in coastal environments. And so we worked with NOAA and a whole range of researchers for over a 2-week period last fall to really build a very big digital elevation model for this area. It's on the upper right. It's called Boundary Bay. We are only going to start working with the Shemayamu First Nation because they're being impacted by sea level rise right now. Their coastline is retreating. They want to know what their future is like and how storms will impact them. But because of the group of people we brought together, we were able to, not me myself, but the team was able to provide a 1-meter digital elevation model from south of the border all the way up to North Vancouver. That's going to be used for purposes of understanding the impacts of storm surge and sea level rise on the coastline. Let me move to the project that Manu was talking about, carbon removal, negative emissions technologies. So in the National Academies had a report on negative emissions in 2019. And they had a whole range, these 4 buckets, the 4 lists I have, you see here. And they only looked at blue carbon as part of the ocean-based solutions. They didn't look at any other ocean-based solutions. And I'm going to come back to the air capture one later. But it was clear that because of that lack of focusing on other ocean-based carbon solutions, that there's now a new study that's ongoing. I've been thrilled to be part of the committee. And it's looking at all of these aspects of ocean-based carbon removal in terms of is the technology available? What are the environmental impacts? What's the cost effectiveness? How much carbon removal does it provide in terms of potential? And that work is ongoing right now, and there'll be a report coming out. In terms of Ocean Networks Canada, a lot of the technology associated with these carbon removal aspects are in the laboratory stage, excuse me. And so Ocean Networks Canada, some technologists have already, for example, for ocean alkalinity enhancement, have already come to us to move it from the lab stage to mesoscale or to a stage in the real ocean environment. So we are interested in really partnering with companies, and if you are interested, we would be happy to talk with you to provide that platform to either help to develop it or to demonstrate it. Excuse me. So let me just talk about this last one, air capture and seafloor carbon mineralization. There's probably a 250 teraton reservoir capacity. I just need a glass of water. Excuse me. And so we decided to work with Columbia University and others on this negative emission technology. Most of you know this is a stylized diagram from the UN Energy Program, where the darker blue shows that we have to start reducing our emissions drastically, which is still not happening. And the lighter gray that's after 2038 means that we are going to need negative emissions to keep us below 1.5 degrees C. So instead of just, whining about it, we decided to move forward to see if we can develop a technology. And Climeworks in Iceland worked with technologists to put direct air capture using energy from the geothermal plants to to inject CO2 into basalt on Iceland with success. And there's been a couple papers, one in Science quite a number of years ago, that demonstrated that the mineralization of the CO2 they captured, some of it was direct air capture, became mineralized in approximately a few years, which is very durable sequestration. Then most recently, that was reconfirmed with further confirmation of this in a paper last year in Nature. So this was, to us, was really important from a solution perspective. And so we've proposed to develop what we call solid carbon, combining ocean platforms, hopefully powered by renewables, or some combination of reduced emissions, less than what we're pulling out of the atmosphere, and then pumping that CO2 that's direct air captured through the water column and then into the seafloor ocean basalt. And because what we're seeing is that basalt, because of the size of the reservoirs on the planet, much larger than the size of the reservoirs where we're pulling oil out of the seafloor, like giant size compared to that, but also because that reaction with rock takes place and means that it is really a durable solution for negative carbon emissions. And this is what a stylized image of what it could look like. We're looking at all kinds of options. So for example, we could take existing technology that's used right now in the Gulf of Mexico for the Stones production facility, which is in 3 kilometers of water. It has a floating production, storage and offloading vessel that is actually pulling oil into the big platform in 3 kilometers of water connected to the seafloor. And then there's shuttles taking that oil back to market. But it's simple enough, really. And it's a lot easier actually to just simply do injection and production in these systems because of the shallowness of where the basalt is in the subsea floor. And we could just simply do that today. It's expensive, but it could be done today. But we're looking at all options in terms of this. We were funded by the Pacific Institute for Climate Solutions last year to actually conduct a feasibility study over the next 4 years. We're now in our 2nd year. And I'll explain the aspects of that in a minute. We also put in a competition in the MacArthur Foundation Top 100 and Change and made the top 100. We weren't selected as a finalist, but we were showcased and we have gained quite a bit of interest because of that submission to MacArthur Foundation. And we have an increasing number of partners, mainly Carbon Engineering, who is a company in British Columbia, based in Squamish, British Columbia, who has a direct air capture technology. They're partnering with us. As I mentioned, Columbia University, University of British Columbia, University of Calgary, University of California, Santa Cruz, some teams in Germany, and it's growing as we gain momentum in this project. And one of the reasons that Oceanography Canada is involved in this is because this location on the Neptune Observatory called Cascadia Basin, it is the best characterized serendipitously because of a lot of work over the years with the ocean drilling program and the integrated ocean drilling program, and now the International Ocean Discovery Program. There are boreholes there that already exist, and we have real-time monitoring. And so, in fact, there was Andy Fisher from the University of California at Santa Cruz actually conducted a hydrogeology experiment in the basalt at Cascadia Basin. So it's the basalt we're in about just under 3 kilometers of water. There's only about 300 to 400 meters of sediment, and then you get into the basalt. So it's a much easier kind of situation than a deepwater production system in 3 kilometers of water. So this is the ideal situation to demonstrate the efficacy of injecting direct air capture carbon CO2 into ocean basalt. And that's going to be our next step. What we're doing in the feasibility study right now, we have 3 groups. One looking at the technology, what combination of existing technologies or new technologies do we have to do research on to actually get that ocean platform or system together. The second group I'm leading is looking at developing the plan for the demonstration project at Cascadia Basin, and we're pushing on that hard to accelerate that because we know that once Iceland actually did their demonstration project,
they have now started to have investments coming in to accelerate the development of technology, which is what we want to do. And then the third group is looking at all those aspects that we typically as a science community and engineering community ignore until the last minute. We're looking upfront at acceptance by the public, regulatory acceptance, and investor acceptance. And the actual, even if we just looked at the potential in the Cascadia Basin alone, which spans both the US and Canada, there's over 750 gigatons of reservoir capacity in that location alone. And there are many other basaltic locations of these kind of ages, typically in the Pacific, but in other locations on the planet, that would also serve as basaltic reservoirs for direct air capture. So one can imagine, I hope we can imagine, is that an industry could grow out of this, just like the offshore oil production industry grew and really became a very profitable industry, although it, through the burning of fossil fuels, the outcome has not been good. But the same kind of industrial development could happen around this combination of technologies. And so, as I mentioned, we have team leads in these engineering, natural sciences, social sciences, and that there's a growing number of partners that you see on the left. And then this is our timeline. We had a pre-feasibility study with Columbia that they led with US Department of Energy. And we're currently in this feasibility study of those three aspects I just talked about. And so that's just a high-level summary of solid carbon and some of the other solutions we're working on. If you want to learn more about us, we do an annual report for our society. Our nonprofits are called societies. And last year's annual report was focused on ocean intelligence that describes some of these activities that I just talked with you about, and you can get that from our website. So I'll just close there, and I'd be happy to answer questions. We're going to break into groups. And Manu, I think I remember the first question was, what do we want to know is there, in terms of how do you think you could contribute to advancing the solid carbon project? What technology could you provide? And Manu, I can't remember the second question, I'm embarrassed to say.
Don't worry, I can read it out. The second question for the discussion was, what do you see as the main issues that you see for the public and government to accept these solution strategies? Essentially, what do we need to do in order to have acceptance from the public and governments for this type of technologies?